consider stacking constraint and stability constraint, as well as some integer formulation for special cases with identical container sizes or with identical container weights. Here, let me quickly jump to the results, as I want to make a comment on the computational results we obtained before moving on to the math heuristic. We evaluate the model's performance using the 405 instances proposed by Roberto and Pacino in 2018 for the basic model. And we adapted these instances for the rest of the models. We observed that the difficulty in solving the problems increases considerably as container different sizes and the stability constraints are included. And the combination of both characteristics makes the problem very difficult to solve. I will not explain the BSW model in detail, but just point out that it consists of two variable sets, one describing the layout of the seat at each port, and the other the relocation at each port. The constraints of the model can also be divided into two groups. The regardless group identified and productive moves at each port and involves constraints 2 to 5. This group relates variables describing the layout to those describing the relocations. The storage groups ensures a proper stowage and involve constraints 6 to 16, because these two last constraints ensure the stability of the seat. We follow the approximation described in the thesis, in the doctoral thesis by Pacino. Here, stability is related to the position of the center of gravity. Constraint 15 limit the position of the longitudinal center of gravity within a given threshold, and 16 forces the vertical center of gravity to be below the center line of the vessel. So, since the integer programming model don't provide satisfactory results for real size instances, we thought about developing a matheuristic algorithm. And by using the structure of the BSW model, in which there are two sets of variables, one describing the configuration of the seat and the other describing the relocation, we propose the use of an insert and fix algorithm. The insert and fix is an iterative procedure that solves at each iteration a problem that is a subproblem of the original. Let's look at our example root again. All these variables form the BSW model. To explain the algorithm, we consider that variables highlighted in gray are not part of the subproblem being solved. In the first iteration, we consider the problem of minimizing the relocation at port 5 and 6, considering the stowing plans at port number 4, 5, and 6. Binary variables are indicated in blue. We solve the model, and a subset of variables that have been declared as binary in the previous iteration are set to the value obtained. The variables already set are highlighted in red in the figure. Moreover, a new subset of variables is added to the problem and declared as binary. We solve a new problem, the problem that considers the stowage plan at port number 3, 4, 5, and 6, with port 5 and 6 fixed, and fix another set of variables and add a new set of variables to the new problem. We solve the problem again until the solution provided in one iteration provides a feasible solution to the problem, since all the variables involved are declared as binary or are fixed. So the solution of this problem, the last iteration, is a feasible solution to the problem. In order to obtain better results, we developed a heuristic algorithm that provides the solver with an initial solution at each iteration. In the first iteration, a specific heuristic provides the layout at port n-1, taking into account that only containers going to the last port are aboard. In this case, it provides the configuration at port number 6, considering that when the ship leaves port number 6, there are only containers going to port number 7 aboard. And in the following iteration, the heuristic procedure copies the layout of the ship in the next port and switches it to the current port. First, as many containers as must be loaded at the next port are removed from the layout, and then the empty slots are filled up with all the containers with delivery port, the next one. And finally, our algorithm properly repairs the solution, preventing 20 containers on top of 14 containers and ensuring the stability conditions. Let's see the computational results. We coded the algorithms in C++ and we ran it on a single thread using C++ 12.10. As I anticipated, we used the 405 instances from Roberto Pacino, in which the seal is full in all ports. These instances are divided into 5 groups: long, short, long, mixed, authentic, and required. The number of ports between the port of load and the port of discharge is on average small in short instances, large in long instances, and follows random distribution in mixed and authentic instances. The required instances are more challenging since they were generated to force rehandles or relocations. Since these instances were generating to the basic problem, considering only one size of container and no stability constraints, we adapted them to consider a more complex ship structure and weight and size related constraints. We consider a ship with 10 bays, the number of rows varying between 5 and 25, and the number of tiers varying between 6 and 10. The ship capacity ranged from 600 to 5,000 TEUs. This table shows the results obtained by the insert and fill algorithm, considering 1, 2, and 4 hours of maximum running time. And it also shows the solution obtained by the fully constituted algorithm here, and by the model given an initial solution provided by here. We refer to the model with an initial solution as BSW star. Launching the BSW model with initial solution, we see that no satisfactory results are obtained, since in most cases, C+ does not manage to improve on the initial solution due to the high number of variables and restrictions involved. It only improves the average number of rehandles by 6%. The insert and fill algorithm obtains an average of 55 rehandles in an average by considering a time limit of 1 hour, and it cuts the number of rehandles by 13 and 25% with time limit of 2 and 4 hours respectively. And focusing on the number of ports, the results reveal a significant increase in the difficulty of the problem as the number of ports increases, dramatically increasing the average number of rehandles. The insert and fill algorithm solves all the instances of 6 and 8 ports in short, mixed, authentic, and log groups with an average of 8.7 relocation. However, the average of rehandles is 40.9 for the 10 port instances in these groups. I have not added slides comparing the base model with the existing model in the literature, but it outperforms existing models. So in talking about future work, we will focus on developing new techniques and other matheuristic approaches that will not rely on the performance of integer programming solvers. Another direction will focus on adding practical constraints such as the system of refer container, IMO containers, the system to consider a more precise zip structure, including Hadj cover, as well as the study of the stability of the zip with physical equations. And that's all. Thank you very much for your attention.
Thank you, Consuelo, for the talk. Is there any question? Jose, please.
I was just clapping.
So no question. Okay.
I have a question. Sorry.
Oh, sorry.
Thank you, Consuelo. Really nice presentation. I like it a lot. Several years ago, I used the insert and fixed for the bin packing. So I have a question. Maybe you said it, but I missed it. So the idea is that at every step of the process, you consider some ports, and then you fix some decision that you made for them. How many ports do you consider at every step? And among those, how many decisions, I would say, the decisions of how many ports do you fix at every step? You are muted.
Yes, at its sub-problem, we consider the stowage plan of 3 different ports.
Okay.
And therefore, if we consider the stowage plan in 3 ports, we are considering the relocation in 2 ports. And we solve the problem of fix the stowage plan at 1 port.
Okay. And did you try to change those 2 parameters?
Yes, we try to change it, and we also trying to swap the order. I mean, we start from the latest port to the first port, but when we swap them, the performance was worse.
I guess it makes sense considering the structure. I mean, if you fix the last one, then it will be below on the stack. So it makes sense. If we consider a greater number of ports in its problem, what happens is that there are so many variables on the performance. The integer model is very bad. And this is another question, but once again, maybe I missed that because you show a table with all the results and everything. But my question was about the time that you need to solve every step. So for 3 ports, does it take a long time or?
It depends. It depends. It depends on the lower bound of the solution. But here, when we solve the problem with 1 hour, what we do is the first step, we don't give 1 hour to the solver. We give 1 hour divided into the number of iterations that we will do. Okay. But you need the amount of time that you provide. Yes, yes, most of the time we need.
Okay. Because maybe an idea would be, I don't know, because if you use the insert and fix, maybe you know the relax and fix also, so you can relax fast. So it maybe speed up the process.
The relax and fix fails because there are the problem becomes very, very big.
Yeah.
The fractional relax and fix shows a similar performance, the insert and fix, but we did a large number of computational results, and the insert and fix of the better improvement.
Okay, nice work. Thank you for the presentation.
Thank you.
Thank you again, Consuelo. So we move to the second talk that will be given by Khadija Salem, and the title of the talk is The Integrated Production Planning and Cutting Stock Problem in Home-Textile Industry, ILP Formulation and an Epsilon Constraint Approach. So please, Khadija. We see the screen, but we cannot hear you.
It's okay now?
Yes.
Thank you. So, I am Khadija. I am as a postdoctorate at ESICUP. And today I'm going to talk about the integrated production planning and cutting stock problems. This work is joined with Elsa Silva, Professor José Fernando Oliveira, and Maria Carravilla. So, don't know what happened. Okay. I'll outline the outline of my talk of today is the following. We started by introduce the context of home-textile industry. Then we formulate, we give a formal definition of the problem. Then the different proposed mathematical model, as well as the epsilon constraint to tackle this industrial problem in its mono-objective and b-objective variant. Then we give some experiment, and finally our conclusion and some future direction for this work. So let's start. In general, the process of from home-textile industry is summarized in more than 6 phases. But in our case, we are interested in just in 4 of them, as the following. For the first 3 phases are dedicated to the production part, and the cutting phases are dedicated for the cutting part. So as we see here, in the weaving phases, all the fabric rolls are produced in industrial loom. Then are dyed in bathtub, where they accurate the final color. In the printing phase, drawings of 1 or more colors are produced in the fabric rolls. We can say that this process is optional, as the customer might decide in plain or patterned products. And finally, the process ends at the cutting phase, where the fabric rolls are unrolled and folded in the layer in a cutting table and are cut following a cutting patterns like here. Here we have the different layer. For example, here we have 6, and here we have the length for each cutting pattern, which means a cutting pattern represents the layout of the pieces here in the layer. And just I forget some things in this process. An intermediate fabric rolls from the stock can be used during all the process. Now we move to describe our problem, but before this, why we are interested in this problem. A central theme of this study is to propose a novel way for modeling the production planning together with the cutting restriction using integer linear program. Let's start by an example. We given a set of 3 fabric rolls with a fixed width, WJ, as the following: 160, 200, and 225. A set of 5 items with the different characteristics given in the following table regarding the width, the length, and the demand. In our case, we consider as dimension for the cutting table PMIN 65 and the PMAX 500. An optimal solution for this instance is the following, in which only 2 fabric rolls are considered, which means the first one with the W1, and here we can see we have 2 cutting patterns from this fabric rolls, with the smallest part here is related to the waist, with a length 920, and we consider also the third one, and we have 2 cutting patterns from this one. That I said all the shaded rectangular are the waist. So, as previous work to this problem, to the best of our knowledge, the only work is from Silva et al. Since 2015. they considered a general variant of this problem, which means in 3 stages, guillotine and with trimming, and this they consider a real problem from a Portuguese home textile manufacturer company. In their case, the manufactured product must be identified by 3 references that I presented in the process. Each reference is dedicated to each production phases, weaving, dyeing, and printing. And that I mentioned, an intermediate stock can be used for each weave in a reference TC. Also, we have a limited in the maximum height, which means the number of layers. And our objective was to minimize the fabric cost, including the production cost, also the cost from used textile from stocks, and the cost of the cutting, the cost of the cutting the patterns. They proposed a mixed integer programming model solved by column generation methods, where all the possible cutting patterns are known in advance, generated using a constructive level packing heuristics. And the pricing subproblem in their case was a 2-dimensional knapsack problem. They did some experiment in just one real instance from the Home-Textile company, but in this instance we consider 18 piece type with 4 different references TC and 20 fabric rolls, and the demand is really a higher number between until 1,750 demand. And they consider also a different scenario by, for example, increasing the minimum dimension of the cutting table, or the variation of the minimum length to be produced, and different costs for the stocks. So in our case, we a little bit updated the problem. So our integrated problem can be formally given as follow. We consider as an input a set of pieces type, in which each piece type has a negative width and length and a positive integer demand. We consider also a set of available negative width dedicated to the fabric rolls. Our objective is to determine the length of produced fabric rolls with references R. Here is the difference, because in our case we consider only one references that combined all the 3 references for the 3 phases from the production process. And we aim also to determine the set of generated cutting pattern. And for each cutting pattern, we define the dimension in terms of width and length, and we give also the set of composite pieces. In our case, we first try to minimize the textile material waste, which equivalent to the textile material used in the production process. And in second time, we will consider the number of generated cutting patterns. So for this reason, we tackle the problem on two dimensions. The first one is the mono objective. We minimize only the waste, and the second dimension, sorry, it's to minimize the B objective. The B objective problem, both that I said, the waste and the number of generated cutting pattern. So before going to present the different model that I proposed, here just we give the different constraints to be respected in our case. All the cuts must be of a guillotine type. About the number of stages, in our case, we consider 2 stages. And we consider also 2 cases based in the way, based in the last stage, the trimming, which means non-exact and exact APP-CSP. All the pieces have a rectangle shape. All the pieces also must be cut to serve all the demand, which means we have exactly the demanded or the requested demand. No overlapping between pieces type. Also, we have a fixed orientation. In our case, all inputs are deterministics. And we assume also that the pieces are sorted by decreasing order of the width, and then and after by the length. and about the limit, no limit number of cutting operation. So according to the topology of Forscher, AL 2007, our problem, the integrated production planning problem and two-dimensional cutting stock problems, can be considered as in the part of the cutting stock as open dimensional problem. Why? Because the width of the roll is fixed and the goal is to minimize the total length used, which means in our case the total length to produce. Also, we can consider also the two-dimensional multi-type stock size cutting stock problems, and because in each cutting table, different length can be defined for the cutting patterns, meaning that the large object of different size need to be cut, but also all the piece type are weakly heterogeneous. So just here is our position versus the CP problems. So we move now to the to present the different ELP formulation that I proposed. We first consider position-based DLP formulation, in which two parts are considered. The two first variable alpha and x are dedicated for the production part. One is an integer one. Xj is the integer variable about the number of meters to produce for each given width, and alpha j is a binary variable and equals to 1 if there exists a production with the width wj. For the CSP part, we consider four variables, in which one is integer, is the yjp, is the length of the PM cutting pattern of width wj, and the other are dedicated for the different stage in the cutting, which means the beta is for me is dedicated for the cuts from the stage 0, which means the cutting patterns. Gamma is about the stripes, and delta is about the pieces in the second stage. The main constraint in our case to be respected are the minimum production quantity given by the LMIN, also meet demand of all customers, and we have some geometric constraint of the cutting process that I said, the two-stage guillotine cuts, and also respect the dimension of cutting table. Our objective that I said is to minimize the total textile material, which means also the waste in our case. And the different constraints are given by the following inequalities, in which the first two are for the, that I said, for the dimension or the bounds for the production phase. Here are just, the third one is the precedence between the cutting patterns. 4 and 5 are about the dimension of the cutting table. Here is about the length of production. And from 8 until 11 is about the cuts and the first stage that I said about the stripes. From 12 until 15 is about the cuts and the second stage, and our relation and their relation to the cutting pattern, and also to respect the length for each generated cutting pattern. And at the end are only to ensure the bound related to the demand. From this integer linear program, we extended two other variants. I will explain after how, but now we move to the beam packing based ALP formulation. In our case, we consider here only two binary variables, and we consider the same as before about the integer one about that I said about the number of meters to produce it with the width wj and the length for each cutting pattern. In our case, alpha and beta are used to represent the relation in the first time between each piece type and stripes, and then between stripes and cutting pattern. And about the main constraint are the same as in the first ELP, and our objective also is the same. Here we give only the set of constraints. The two first are the classical assignment constraint as in the packing problem. Then is about 3 and 4 are about the cutting table dimension. Then is about the limited or the minimum meters to be produced. Then is the relation between that I said between pieces stripe and stripes and cutting pattern, and we respect every time in each the size of each generate cutting pattern. That I said we consider to tackle the mono-objective variant of the problem for ELP, where ELP 2 and 3 are only an extension for the ELP1, which means here we consider the same variable for for the production planning problem. We consider only the XJ, and for the SP that I said here, we just update the delta variable to an integer 1, and for the LP3 we consider an alternate encoding for the variable related to the second stage. To the first stage, which means to the stripes. And about ELP4, which is the beam packing based ELP, and alpha beta are just to represent the relation between pieces stripe and stripes cutting pattern. We tackle also the problem in the B objective variant, which is the using the classical epsilon constraint programming. Here we consider the main objective is minimize the waste, and we convert the objective related to the number of generated cutting pattern as a constraint by using the epsilon. And my algorithm is the following. So let's move to the experiment. So to evaluate the performance and the behavior of the different proposed model for both the mono-objective and B-objective variant of our problem, we consider 3 groups of instances with a small, medium, or large dimension. And for each group contains 4 classes, except for the medium one contains 8. And for each classes, we solve 10 instances as outlined in the following table. So in total, we have 160 instances. And for the parameters about the minimum length of production, we consider the value 10% from the sum of all the length of pieces type. About the cutting table dimension, we consider, for example, for PMIN, we consider the minimum length of piece type, and for the PMAX, we consider 3 value. For the mono-objective experiment, we consider only 1,500, and for the B objective, we consider 3 value. So in this table, we report the results related to the 4ELP formulation in terms of the average of the Gorby gap, the average of gaps, which computed by this formula, and the number of solvent instances. As we can see here, in terms of the gap, the average gap, we can see that really is the superiority of the LP4, which means the beam packing based model. We can see also in terms of the average gap, both the LP2 and 3 are the same behavior and performs better than the other one. In terms of the number of solved instances, we can see the best one is the ELP4 because, okay, I didn't present the symmetry and the cutting that I integrated for the different ELP, but using the different cutting and symmetry, the second one performs better, but we have really similar results. Then we move to the results related to epsilon constraint. Here we give the number of instances for each Pareto front size for only the groups S and M. That here in the B objective variant, we consider only 80 instances from the generated randomly instance that I presented, and we can and also by varying that I said the Pmax in the interval of the following three variable value 500, 1000, and 1500, and we can see here the majority of instance around between 70% until 80% provided a Pareto front between two with size between two sorry, between 2 until 4 solution, really regarding the variation of the Pmax. In addition, also we can see also that the generated cutting pattern generally varied in the interval of 1 until 7, except in the medium groups we reach until 10 value. Sorry. So maybe this due to the fact that the two objectives are weakly in conflict for this kind of instance. In the same way, we give also some numerical results in terms of the gap for each Pareto front size. We can see here even the average gap between the extreme solution, which means when we have a higher waist and a higher number of cutting pattern, the extreme solution was less than 20% regarding the Pareto front size, with, for example, Pmax 500 and 1000, but correlated to the Pareto with here Pmax 1500.
Sorry, Khadija, you still have 1 minute.
I will conclude. Really. Sorry. So in this talk, we present an integrated production and cutting problem applied to the home textile industry. We gave two variants, mono objective in which the waste have to be minimized, and B objective variant in which both the waste and the number of cutting pattern have to be minimized. We presented several ways in terms to modelize or to solve the problem in terms of ELP formulation and constraint, and we give a numerical validation for the proposed approach. As a future work, we have 3 really axes for me. I will start by the last one because it's my current work now. It's about the study this problem under uncertainty, in our case with defect or under stochastic demand. And I already proposed the 2-stage stochastic program for this problem. I have some preliminary results. And as future work, maybe propose a mathheuristics or meta-heuristic for the deterministic problem or the stochastic one. And we'll try also to propose a data mining based framework to assess the quality of heuristics solution for the our integrated problem. Here just about the FCT related to the Delta CP project. Thanks to the end. Thank you. If you have any question or comment, I have this to answer.
Okay, thank you again. So we have we are very late. We have time for a very quick question, if any. Don't see any questions. So I would switch to the last talk. Thank you again.
Okay.
And the last speaker is Eduardo Machado Silva. And the title of the talk is Computational and Theoretical Analysis of the multi-period cutting stock problem with setups on cutting patterns. Okay.
Hello, everyone. Can everyone hear me?
Yes, perfectly.
Yes. Okay, so my name is Eduardo. I am a PhD student from UNESP. My advisor is Professor Silvio, and I will be presenting the work entitled Computational and Theoretical Analysis, as the professor said. We developed this work in a partnership with Gislaine from UFSCar in Brazil and Professor Kerem from Strathclyde University in Glasgow. The main objectives of this work were to propose formulations for the problem and compare them in a theoretical and computational way regarding lower bound and solution times of the integer problem. This is how I structured the presentation. I introduced the problem, present the formulations, some valid inequalities, the theoretical and computational results, and then I will conclude with some future research ideas. The one-dimensional multi-period cutting stock problem with setups on cutting pattern was classified by Melega et al. As a cutting stock problem with setups on cutting patterns, where the inventory is providing a link between each period. In the author's paper, they provide a review regarding lot sizing and cutting stock problems integration in 3 levels of production. Our problem lies in the level 2 production. That's it. We only consider inventory decisions and demand from the items on level 2 productions. The setup motivation came from the industry environment, where every time we change the knife positions for another cut, there's a charge that is used on the objective function. So we decided to use the setup because of that, and also the time that you stop the process of cutting, and that's stuffs. This is some notation for defining the formulations. J will be the set of feasible cutting pattern indexes, and the upper bound of the frequency of the cutting patterns, ST the cost for cut, HIT the cost for holding items, C the material, and AIJ the number of items cut of the number of items I cut in pattern J. The first formulation is an adapted version of the Gilmore and Montgomery. This formulation resembles the classical lot sizing formulation of Wagner-Witting. Here we have the production of items that now are considered by the product of the frequency of the cutting pattern J and the number of times item I was cut, the setup on the cutting patterns, the domain of the variables, and the objective function that we use for all the formulations that I will present is minimizing the inventory costs, setup costs, and the number of objects that were cut. The second formulation is adapted from the Van de Beek paper, and it's basically the Gilmore and Montgomery formulation, but now we have NAPSEP constraint 6 that makes the model nonlinear due to the demand satisfaction constraints, and we just linearize it using the strategy presented in Hadj et al. The third formulation is adapted from the pattern minimization problem of Johnson and Sabingila. It basically is the Van der Beek formulation, but they propose a new model, a new idea of linearization for this PMP problem. So we just extended that for the multi-period environments and use it. The next formulations are all based on the arc flow formulation. The basic idea that the cutting stock can be seen as a network flow was introduced by Usey, and later Valério de Carvalho also presented a formulation that is called the arc flow formulation. It's basically consists of seeing cutting patterns, feasible cutting patterns as a path in a cyclic graph of L+1 nodes, where L is the capacity of the large object. This is just some illustration. So from the Valério's arc flow, we derived 3 three new multi-period formulations for our problem. The first one is based on the pattern minimization arc flow, also presented by Alves and Valerio in 2008, that we extended for adapted and called AAF, adapted arc flow. This formulation is already, as all the previous others are already showing the literature of the cutting stock problems and integrated lot sizing problems. The second one is adapted from the Johnson-Sabingela formulation, where we changed the knapsack constraints by the flow conservation constraints, and then we extended that as arc flow in a multi-period environment, deriving this AFGS formulation. The third one is basically the improved version of the arc flow that was presented in Delorme-Niori, that reduces the number of nodes of the arc flow formulation, improving the time for solving the problem. So we basically extended the previous two formulations in a reflected environment, as described in Delorme-Niori. Just to outline the basic ideas of the reflect formulation, as the name states, it reflects arcs and uses just half of the capacity of the nodes. That's it. We just use L/2 nodes, where the node L/2 is the reflect node. And the formulation will keep the arcs starting and ending before the reflection node, while it will delete the arcs starting and ending after the reflection node, and it will reflect the arcs starting before and ending after the reflection node. So you just have to increment a new index indicating that this is a reflect arc, and we can have a CSP formulation as well. From the lot sizing problems, we have the no facility location. Is already proved that for the multi-item uncapacitated lot sizing, this formulation tie the convex hull of the problem. And therefore we decided to extend the idea for the multi-period with setup on the cutting patterns problem. This is the AGG facility location reformulation. We call it AGGFL. And the other formulations are extended in a similar way, but now you have to deal with non-linearities. They essentially came from the link constraints 10 and the demand satisfactory constraints 12. So we just linearized them and got new formulations. Also arriving from the lot sizing problems, we have the LS inequalities, and we also adapted them to a cutting pattern environment and used that then on our problem. So I will state some theoretical results about those formulations just presented. As a notation, I would use ZLP to denote the lower bound of the linear problem, XLP as the feasible region of the LP relaxation. Just to outline the formulations and the names, we have the adapted Montgomery that is extended to facility location Montgomery, the Van der Beek extended, Johnson extended, and the arc flow Johnson that can be extended. Basically, our idea to introduce Johnson arc flow was so we can extend that in a facility location way, because the adapted arc flow can't be extended since we don't have a cutting pattern representation in the formulation. The first and the second theorem basically states that the AGS provides a better lower bound than the AVB. And theorem 2 states that the AFGS provides a better bound than the AGS. The proofs were made using projections into the LP spaces of these modules. The third theorem is it came from the cutting stock literature. Valerio already proved that the arc flow model provides the same lower bound as the AGG formulation. We applied a similar idea to using dancing of the composition to prove the same result for the multi-period cut stock with setups. The AGG provides a better bound than the AFGG. We use AFGS. We use the same idea of dancing of the composition. And as a consequence of those theorems, we got this theorem 5, that sorts all the formulations just presented regarding their Larenbaults over here. And now we have some consequences deriving from the lot sizing problem, that the extended formulations provides about at least equal as the original formulation, and also arriving from the lot sizing problems that the LS inequalities when applied to the original formulation provides the same bounds as the facility location reformulation of the lot problem. So we prove that this is also true for the multi-period cutting stock with setup on cutting patterns. Okay, this is some information regarding the computational results. We used Seplex 12.9 and coded the models in the Visual Studio 2017. The pattern-based formulations were solved using a column generation technique, and we tested them in 100 instances, equally divided in 5 classes. Those classes differ basically by period and number of items. This is the parameter setting table where we use the values. And the first table states the values of the LP relaxation, the average LP relaxation from each class, and the average time for getting the Larenbault. For each column, we denoted by red the worst performance and by blue the best performance. As we can see, the pattern-based formulation attained the better Larenbaults as well for the better computational time. And regarding the worst performance were attained regarding the Larenbaults on the AVB model, and regarding the solutional time on the AFGS facility location and the arc flow formulation, and also the AGSFL. The next table is basically the same idea from the previous one, but now with the IP solutions. And since now we are dealing with upper bounds, the idea from red and blue just changes right now, because the red is the worst performance, and it is basically, sorry, now we want that as bigger is not good. Bigger is not, since we are dealing with upper bounds. So blue is the better the better results, and red is the biggest, that is now the worst results. The worst is not fair to compare since they are heuristic method used to solve the pattern-based formulation, but the worst solutions, IP solutions, were attained by the pattern-based formulations, while we also got some bad results in the AVB formulation for class 2 and 3, and the AAF, due to the increasing of number of arcs, got bad results for the class 4 and class 5. Regarding the computational time, all the formulation attained the maximum time, that was half an hour. I forgot to mention that, sorry. And as for integer solution, we got the better results on the facility location Van der Beek, and the facility location Johnson and Sadingela arc flow, and the facility location Johnson and Sadingela normal original formulation. This is a table showing the Seplex gaps. The best gaps are obtained by the reflect formulation of the pattern minimization problem, the AAF, and the worst are obtained by the AVB solution. And since class 4 on class 4 the AVB did not get feasible solutions, the worst performance was from the AFGS, probably due to the amount of arcs used to solve the formulation. So as a conclusion, even though it's not fair to compare, but the AGGFL is solved by heuristic method and obtained the best computational performance and also the best Larenbaults for the problem. The R formulations provides a good computational time for solving the instances. when compared to other formulations, except from the pattern-based ones. The AGS obtained better performance than the AFGS, even though the AFGS it's extension with better lower bound than the AGS. However, the AFGS facility location obtained good integer solutions and a stronger bound. The second stronger bound, except from the reflect formulation and the pattern-based ones. As future research, we intend to improve the literature review and present some new formulations for the problems and compare them as well in the theoretical and computational way. Implement some exact approach to solve the column generation, the based formulations. And we want to improve our computational tests by varying the value of L and the trade-off between setup and venture costs. And develop heuristic methods based on the characteristic of each model. Basically, that's it. This is some bibliography that we use it on the work. And thank you for your attention.
Thank you, Eduardo. We have time for a question. So is there any question from the chat? Don't see. I have a very quick question. At some point, you showed some computational results for the integer problem, and
yes,
where you presented the solution values and the computing time. So the computing time were referred only to the instances that were not solved to optimality, or all the instances?
All the instances. They actually, since we are
the next one.
Oh, sorry, the next one. Yes.
So AGG, a facility location, has a computing time which is on average 0.22.
Yes, but this is solved by a heuristic method based on the column generation. So it's not the optimal solution. It's not solved to optimality.
Okay. I see. Okay, so it's not an exact formulation. It's just an heuristic one.
Yes, just the other ones that were solved with the limitation of time, but the only heuristic were the AGG. And
sorry, another question, probably something I should know. In the Van der Beek formulation, you linearized some constraints in which you had the product of variables, right?
Yes, it's on the demand satisfaction constraints. I linearized that. The constraints over here.
So the variables are integer, binary, or whatever.
The XJT is an integer, and they are both integer.
Okay, so linearization is easy, no sense.
Yes, we basically binarized the XJT and used the usual strategy for linearizing the product over here. It's presented on the Hadj arrow, this method.
I see. Thank you. Is there any other question? So I thank you again, and thank all the speakers again.
My pleasure.
And thank all of you for being here, even in the very last evening or afternoon, depending where you are. And so I think the section is over. We can meet tomorrow. And we join all Jose for the clapping, for the virtual clapping to all the speakers. Okay, see you tomorrow. Bye-bye.
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 Thank you, the speakers. See you tomorrow.
Bye.